Okay, so we're going to go ahead and start this chapter. We're going to start straight with chapter 16. Okay, proteins are biomolecules that contain many amide bonds formed by joining amino acids. And so remember the amide group, that was when you had the carbonyl attached to a nitrogen, and the carbon was the carbonyl carbon versus a regular carbon as we see in the amine group. Okay, so here's an example of an amino acid. And so a bunch of these amino acids are joined together to make your protein. So here they're showing you the amide group or the amide bond right here. And essentially it's between the carbonyl carbon and the nitrogen right there. Okay. Uh, I have a little bit of sinus headache today, so I might not be as high energy, but I will try to power through. So here we have a protein. Once again, you can see here this protein is made up of many amino acids. So someone asked me, it's hard for me to visualize the amino acid. The easiest way I visualize this is from the central atoms. If you look over here in the amino acid, we have a nitrogen attached to a carbon, attached to a carbon, right? I mean, of course, there's more to it than that. But when I look at the protein, I'm looking for this combination of central atom, NCC, and that marks the boundaries of the amino acid I'm looking at. Now, of course, over here, look at that. Well, the N is missing here, so that may not be so helpful. We can start from this one here, NCC, right? Essentially over here, we're seeing an amino acid there, amino acid there, amino acid. So from the structure here, at least see 3.5 amino acids. I'm assuming, of course, there's a nitrogen here, right? So that will be 4 amino acids. And of course, we're going to be characterizing the amino acid based on this R group here. So you see how you have R1, R2, R3, R4. This is just showing you that the amino acids will be different at those R points, the rest of the molecule, where you can have maybe other functional groups as we can see on the right. Let's go ahead and move on. Proteins account for about 50% of the dry weight of our human bodies. They perform many functions in the body, right? Unlike lipids and carbohydrate, proteins cannot be stored, so they must be consumed daily. Okay. Current recommendation of daily intake for adults is 0.8 grams of protein per kilogram of body weight. More is needed if they're in children, because children are still growing and they're growing faster than we are, so they have to eat more protein. Meat, fish, beans, and nuts are all high in protein. These are all high protein foods. So we have a picture here showing us the different functions of protein in our bodies. This is a very important. Proteins transport oxygen in the blood. The name of that protein is hemoglobin. Collagen. This is a fibrous protein in connective tissue found in tendons, bones, cartilage, blood vessels. Collagen is also used to keep people youthful. So people who are working out a lot will take collagen to repair their torn muscles but also remain youthful. Ferritin is a protein that stores iron in the liver. Please notice the names here. They all, not all, but most of them end with EN or IN. Hemoglobin, collagen, ferritin, actin, myosin, keratin, myoglobin, insulin. So most of these have a suffix in the name, even though they're common names that ends with IN, just FYI. Okay, we have actin and myosin fibers. These are proteins that control muscle contraction. We have keratin, a fibrous protein that's used for hair, skin, and nails. Myoglobin, a protein that stores oxygen in tissues. Insulin, a protein that regulates blood sugar, right? It's synthesized in the pancreas and it regulates blood sugar. So we can see protein has a very, very important function. Okay, now we're looking at the general features of amino acids. Remember, a bunch of amino acids connect together to make our protein. So I'm writing them here as amino acids. The amino acids in our polymer called protein act like pearls in a pearl necklace. They're connected, like we saw with other macromolecules, to form, in this case, protein. Amino acids contain two functional groups. On one end, we have amino group, amino derived from ammonia, NH2, and the carboxyl group from the carboxylic acid. Remember this group right here, COOH, is carbonyl, attached to a hydroxide. Okay, so here we're looking at a generic amino acid. We have a carbon in the middle. On one side, you have the carboxyl group. All amino acids have a minimum of carboxyl group, a carbon in the middle, and then we have an amine group, a hydrogen on top, and the R group. Now, the R group is different for different amino acids, as you can see on the right. I haven't addressed those yet, but I'm still just trying to talk about the generic amino acid structure. So on one end, you have the carboxyl group. On the other hand, you have the amine group. And then you can see right here, we have this carbon in the middle. Now, if the surrounding groups are all different, the carbon in the middle will be chiral, like we've seen before. For right now, the generic name for this carbon is alpha carbon. The alpha carbon tends to be the carbon attached to, the carbon closest to the functional group. So this carbon here is closest to both functional groups, amino and then the acid, ergo amino acid. Okay. Okay, the simplest of all amino acids is called glycine. This right here is glycine. In the glycine molecule, the R1 or the R part, the rest of the molecule is essentially hydrogen. For that reason, this carbon here is not chiral because these two groups match. For the carbon to be chiral, it has to be surrounded by 4 bonds, 4 single bonds, and each group attached to that bond has to be different, right? So we have glycine, and then we're told here the R group, called the side chain, determines the identity of the amino acids. If R is a basic nitrogen atom, it is a basic amino acid. So essentially, not only does the R group that's right here, could be an element or a whole group of elements, identify the amino acid, it identifies the type of amino acid that we have. We tend to have neutral amino acids, basic amino acids. So we have either, for the amino acids, we have neutral, we have basic, and we have acidic. So it's the R group right here, whatever that group right there, that will determine whether it's neutral, basic, or acidic. So we're being told if R is a basic nitrogen atom, then the whole amino acid is called basic, according to the R group. If R is an additional acetic acid group or acid group, then that whole amino acid is classified as acidic amino acid. Okay? So the group right here determines the identity of the amino acid, but it also determines the type of amino acid we have. And then the types we have to pick from, we have neutral, basic, and acidic. Okay? So let's go ahead and move on. General features of amino acids. We're told here all amino acids have common names, which are abbreviated by either 3 or 1 letter designation. For example, the glycine we just saw, where the R value was essentially hydrogen, is often written as GLY. Remember, chemists are very busy people / lazy. They don't want to have to write the names all the time. Sometimes they're dealing with proteins that have a lot of amino acids. If that's the case, they don't want to have to write the full name all the time. So when convenient, they might use the 3-letter abbreviation or the 1-letter abbreviation. The longer it is, the shorter or the less they write per amino acid. Okay? 20 amino acids occur naturally in proteins. Humans can synthesize only 10 of the 20 amino acids needed for proteins, right? So the rest of them we have to consume. We can consume from plants or from animals. The remaining 10, called essential amino acids, must be obtained from your diet and consumed on a regular, almost daily basis. Okay? People who are vegetarians usually struggle a lot. Vegetarians, or what's the other thing? I don't know. I just went blank. I took some medication for my sinus, so now I'm kind of getting a little drowsy. But yeah, people who are vegetarian, let me stick with vegetarians, they tend to struggle to get enough protein because they have to get enough of the essential proteins that the body needs on a daily basis. Okay, So here we have our amino acids. So as I said, I've put them on the right. So if I need to, I can refer to it without scrolling back and forth, because I'm going to be needing these throughout the chapter. So you can see right here, alanine, also abbreviated. See, this is the R part that makes it different and unique from the others. Alanine, where the R part is CH3. Alanine is abbreviated ALA for the three-letter abbreviation, or A. Okay. Then we have this part here that has a carbonyl. See another amide right here? This is called asparagine, or ASN, abbreviated N. This right here has got a thiol group. This is called cysteine, CYS or C. And then we have another one here that has the carbonyl group, right? The amide group. But it's different from the asparagine because it does have an extra CH2. So CH2, CH2, CO, and H2. This is called glutamine, GLN or Q. Okay? And then we have glycine, which we saw before, GLY. This is hydrogen right here, or G. So while I'm doing this, I know it's kind of getting a little tedious. My teacher in college, grad school, he had us do this exam. Oh my goodness, that exam was so long. I took it for 6 hours. After 6 hours, I was like, forget this. I'm going to take the grade I can get. 6 hours. It was open book. I hate open book exams. Horrible. The ones in grad school, the questions are never straightforward. You can't just go to page 9 and find the answer. It was all this stuff. But anyway, he had us build a long amino acid chain using the individual letters. And I forget the exact message, but it was a class that ended in December. And it either spelled Merry Christmas or Happy Christmas. When I got done, I looked at it and I looked at him and I smiled, and then he smiled back at me. I was like, teachers are so corny. You know, teachers, they have these corny jokes. Anyway, yeah, that's why I do it too. I don't do, yeah, I don't do that. Not with a Merry Christmas thing or Happy Christmas. I don't know. Anyway, so we got glycine, isoleucine. Once again, recognize these side groups. Leucine. You have methionine. Once again, the thiol. And then you have the one with the benzene. That will be phenylalanine, PHE or F. Proline has this nitrogen with a positive charge here. So it's a little tricky, proline. And then we have, let's see, we're still dealing with the neutral ones, right? Then we have serine, that this has an alcohol side group. Threonine has an alcohol. Valine doesn't have an alcohol. Tryptophan, it has this group right here. Tyrosine, it has this alcohol. So now we're moving on to the ones that are acidic. For the acidic ones, we do have your basic amino acid plus an additional acid side group. So these are called acidic, right? You can see here, basic amino acid plus the additional side group. So they're called aspartic acid and glutamic acid. Then we have our basic amino acid, like I said before in the description. This amino acid has a side group that has nitrogen in it. And you can see right here, the nitrogen is positive, making this basic. Well, it's not really that part, but essentially having additional nitrogen in the group makes it basic. Here we have the additional nitrogens makes this basic. Then once again right here, this is also basic, basic. So with the basic amino acid, we have arginine, histidine, lysine. Okay. This is taking me back to the days when I was in school. Anyway, in addition to the amino and carboxyl group, because remember, the amino acid has amino and carboxyl group. Amino, which is why it's called amino, and an acid for the carboxyl group, right? What other functional groups are present in each amino acid? Asparagine. So we have asparagine right here. These are the regular amino acid group. Well, you can see here we have an amide, right? Amide is carbonyl attached to a nitrogen, amide. Here with serine, we have the regular carboxylic group right here, COOH. This is your regular NH3. That makes this one here alcohol. Serine has an alcohol side group. What about cysteine? Cysteine, you have your basic amino acid right here, and this one here is a thiol, Thiol, thiol group. Okay, so moving on. How do the hydroxide groups in serine, threonine, and tyrosine differ? Okay, so I have my hydroxide right here, and I have my carbon, and this is my alcoholic carbon, or my alpha carbon. We'll call it alcoholic. I like calling it alcoholic like it's got a problem, right? This is my alcoholic carbon. How many of the carbons is my alcoholic carbon attached to? Right here. One of the carbons. So this would be a primary alcohol. What about this one here? This is my alcohol group. This is my carbon, my alcoholic carbon, right? And this alcoholic carbon is attached to two other carbons right here and right here. So this is going to be a secondary alcohol. What about this one right here? Oh, this is neither primary nor secondary nor tertiary because it's attached to a benzene ring. When the alcohol is attached to a benzene ring, it can't be primary, secondary, tertiary, because for alcohol to be attached to be classified as primary, secondary, tertiary, it has to be attached to a carbon that has 4 bonds. This carbon that doesn't have any double bonds. The alpha carbon or alcoholic carbon cannot have double bonds. This carbon right here has double bonds. There's certain that use this is a non-majors class. I can't say sp2 hybridized because that's the proper way to describe that carbon. This is sp2, but we're not using those terms, so I'm saying that this carbon here cannot be double bond for this to be classified. So since it has a double bond, it's neither primary, secondary, or tertiary. This alcohol group here is attached to the benzene ring, so it actually has more acidic behavior. Okay, moving on. We're told since amino acids contain base and an acid group, a proton transfer from the acid to the base forms a Zwitter ion. Here's the thing, okay, let's step back a little bit. In general, acids react with bases to form salt and water, okay? Salt, for the most part, is ionic. You see that? So if an acid and a base get together, they form ionic products. So here, though, it's a weird ion formation, and it's not a regular ion as we're used to ions. It's still an ion, but it's a different kind of ion, so it gets a different name, and this is called a Zwitter ion. So the same molecule, amino acid, supplies the acid and the base. So you have reaction within the same molecule to form the salt. Okay? So the acid portion of the amino acid gives up its hydrogen to the base. So you can see here, by giving up its hydrogen ion, not just hydrogen, but hydrogen ion, this part here ends up being negative because it lost a hydrogen and a positive charge. So this creates an imbalance of charge. Now we have excess charge. So if the charge thing is not making sense to you, let me try to illustrate this here. Let's say we had a scenario where we had a neutral compound, right? Like that. And for some reason, like I do over here, I remove one positive charge. What's the overall charge? Please notice, positive neutralizes negative, positive neutralizes negative. Now there is no positive species to neutralize the negative part, so this is going to be overall negative. That's what happens here. When the hydrogen atom and the positive charge is lost, what's left behind here? Negative, because there's no positive charge to neutralize that negative. The hydrogen goes to this side, and the positive charge goes here. Before the hydrogen came, remember, we had one nitrogen, two hydrogens, and then you have these lone pair. The hydrogen comes here and uses the lone pair to form a bond, and essentially the hydrogen comes here, the positive ends up on the nitrogen. Okay, so this is what we end up having. Anyway, salts are ionic. So here, look, we have two reasons. Bam, bam. negative, positive charge to have a salt. Okay, the salt is a neutral form of an amino acid, but the salt, once again, is properly termed a Zwitter ion. Okay, I feel like that could be something that is sold by someone on a commercial. Call 1-800 to get his Zwitter ion. Oh my god, I think I'm getting delirious. Anyway, let's move on. Stereochemistry of amino acid. All amino acids except for glycine have a chirality center because glycine has two elements that are alike. The two H's match, so you can't have a carbon that's chiral. Here we have a chirality center on the alpha carbon, the carbon attached to the functional groups. We're looking at L-alanine and D-alanine. So while we're here, we're being told L amino acids have. So in this case, please notice this carbon here is our chiral carbon, right? So on our chiral carbon, we have an amino acid attached to the left of that chiral carbon. So if the amino acid is attached to the left, this is called L, like we saw before. But L stands for levorotatory, and then D stands for dextrorotatory. Okay. Once again, those names have to do with the direction in which these chemicals rotate plane polarized light. Okay. So L amino acids have the amino group on the left. D amino acids, remember alpha left. D amino acids have the amino group on the right. Okay. So here we're being asked to draw the Fisher projection. That's easy. Remember, the Fisher projection resembles a fish in the sense that the central atoms are drawn as skeletons of the fish bones, right? So this is just simply that. COO minus, NH3 positive, H on top, CH2, CH, CH3. Okay, then we got this one here, COO minus, CH2SH, N plus H3H. That's the Fisher projection. Okay. Okay, so we're moving on. Here we're told to draw both enantiomers of each amino acid in Fisher projections and label them as label them as D or L. I'm just gonna do one. Just one, because whatever we do for one applies to the other one. I think these are pretty straightforward, right? So let me see if I can draw the first one. So I have this COO minus H and H3 CH2, and then my benzene ring right here. Okay, so I'm going to draw my mirror image. I wonder if I can be innovative. Okay, this is not working. This is not working for me at all. I'm always trying to find ways to make my life a lot. No, this is not okay. This is just spinning around. That's not what I'm looking for. Okay, not working. Not working. So I guess I have to draw it myself. Hold on. Okay, so we're gonna have COO minus NH3 plus H. Then here we're gonna have CH2 dash benzene ring. Ooh, benzene ring like that. Yeah. Okay, so this would be the L-amine, and what is it called? L-phenylalanine. Phenylalanine. And this one on the right will be a D-phenylalanine. Okay? Yeah. Based on this This is left, this is right. Left goes with L, right goes with D. Okay? Moving on. So you're going to apply the same principle to the other one. Which of the following amino acids is naturally occurring? Oh, okay. The ones that are naturally occurring tend to be L. So L are more common naturally. Okay. So told name each amino acid and include it as name each amino acid and include its D or L designation in the name. This one here is L, and this is an alcohol. So here's where I have this set up for me. So I'm trying. Ooh, I should make this bigger. I'm trying not to scroll up and down too much. Okay. Okay. Try not to scroll up and down too much. I'm trying to see if I was alone. Okay, I'm not alone. Okay, let's see. I'm looking for one that has alcohol. The ones in the majors class is organized a lot better. I don't know why the one in this book is not. So I'm looking for one that has the side group being alcohol, right? CH2OH. That should be the serine group. There, it's serine. It's exactly serine. CH2OH, right? These are the ones that have the alcohols and then the thiols and stuff. So serine. So L, because this is left, and then serine. Okay? This is right of the chiral carbon. So this is going to be D, and then let me see. I'm looking for one where I have my carboxylic group, right? COO minus. So since I have an extra carboxylic group here, I'm looking from the category called acids. This says neutral. Acid. This one here. Glutamic acid, right? CH2, CH2, COO. Yep. They rearrange the positions of the NH3. Remember, the single bonds have free rotation around the central carbon, so don't worry about that. It's the same molecule. It's just rearranged. Okay, so this is going to be D-glutamic acid. So you can see this is why I have this very close to me, so I can just go back and forth. Okay. For each amino acid, draw the L enantiomer in the Fisher projection. Okay, I'm going to pick one. And then classify the amino acid as neutral, acidic, or basic. Give the three-letter symbol, give the one-letter symbol. Oh, I guess I can do this right here, so I might do both. Okay. They want the L enantiomer. Enantiomer is mirror image. The enantiomer usually refers to mirror images of each other. So they want the other molecule, or it may or may not be the mirror image, but they want the other molecule, right, that has L configuration. So I'm looking at this right now. I'm like, but this is already L, but it's not a Fisher projection. So I'm going to go ahead and draw this out like this. COO minus, H on top, NH3 positive, CH2, CH, CH3, 2. Okay, so I'm going to judge the type of the category, either neutral, acidic, or basic, by that group. Okay, so if it was acidic, I'll have another carboxyl group, a COO group. Oh, this is in the way, my bad. Move this over. But it doesn't have that situation. So what I'm going to do here, let me make this slightly small. Okay, hold on, it's still here. Yeah, and this is still here. Okay. So, yeah, so I'm thinking this is neutral, but I'm going to write it as neutral, and then we see if I'm correct. Neutral, and then this right here, this is going to be L. For me to find this name, let me go ahead and peruse through the neutral. So I know it's not acidic. Let me go up. It's not here. Here they have hetero atoms in the side group. So let me see. I'm looking for CH2CH. Not that. This is basic. Not that group. No, let's see. CH. There. Leucine. This is L-leucine. Okay, so I drew the enantiomer for the first one in the Fisher projection. I classified it as neutral. That's true because it is under neutral. I have to give the 3-letter symbol. So leucine goes with LEU, and then the 1-letter symbol will be L. Okay, so this and that. For this one right here, I just imagine this. This right there is your Fisher projection, and they said make sure it's L. This is already in L format. Okay, so what I'm going to do here for this one is just find its name. So because it has a nitrogen here, it could possibly be basic, right? I'm hypothesizing it could be basic. Let me go ahead and scroll down here and see. CH2. No, this is just one. Yeah, this is just one ring. Let's see. This is tryptophan. So this is classified as neutral, even though this right here is classified as basic. It has to do with lone pairs. This has lone pairs right here that are available, additional to make this. There is some other stuff that we didn't go over because this class is an introductory level class and we can't go into those details. And then right here, you see that this one here has a positive, this has a positive. Usually the other form of this they show us has a positive nitrogen to make it more basic. Anyway, this is tryptophan right here. So L dash tryptophan. Oh, I just realized it was written here all along. Yeah, it's Sunday evening, okay? So the term here is TRP for the 3-letter abbreviation and then W. Okay, we had to memorize this in school, and oh my goodness, we're coming up with all kinds of terminology and stuff to remember this. So we have that, right? And we said this one here is neutral. Okay, so here we're told draw a structure of a naturally occurring amino acid that contains a primary alcohol. Oh, alcohol. So, oh, I'm right here in my alcohol group, right? My alcohol group, amino acid, serine, threonine. This is not really classified as an alcohol, so we're looking at one of these two. Okay, but it has to contain a primary alcohol. And naturally occurring. Naturally occurring is the L one, right? So I'm going to draw this right here. CHCOO minus NH3 positive. I failed to say why I chose that one. They said primary alcohol, right? So here's my alcohol. If I decide to draw this out, you see why it's primary. This is a OH, and there's an H here, and there's an H here. So I identify my alcoholic carbon, and I ask myself, how many other carbons are attached to it? Just one more. That's what makes it primary. Okay, primary alcohol. So that's the first one. Oh, there's many different conditions. Okay, I thought that was it. So this satisfies the first one here. What worked for that was serine, right? Serine. So let me actually make this look a little better. I'll copy this right here. Oops, wait. Can I figure this thing out? Scroll down here. Okay, so the first condition I met contains primary alcohol, contains primary alcohol. That's the first one, right? And that was serine. Second one I'm looking at, it says contains amide. So whatever amino acid you select has to contain amide in the structure. So let me put this down here and then find my amino acid. So I'm going to scroll here. I'm looking for the amide side groups, right? The amide is like abbreviated CON or carbonyl the nitrogen. So is this the end of the list? Oh, no, that's the end. Okay. Let me scroll through here. I'm looking for the amide. That's not it. Oh, there, CON. That's it. Glutamine. So I got C, H, COO minus, NH3 plus. Then down here I need CH2, CH2, CON, H2. Okay, CON is the abbreviation for amide. That's this group right here. And essentially, this is glutamine. And they said the natural form, so this is L-glutamine because I got the amine group on the left. Okay, what is my last one that I have to work on? It says you want to draw an amino acid with an essential amino acid with an aromatic ring. Okay, that one is easy to find. We don't have very many with aromatic rings. Oh, come on. I don't know why it doesn't copy very well. I have to do this twice. Copy. Okay, so I'll leave this small. I hope you guys can see this. Let me make this a little bigger. Okay, so I'm looking for one that has an aromatic ring. That one there, phenylalanine. So I'm going to be drawing L-phenylalanine. And so I'm going to draw C carboxylic acid group here, amine group. Can I fit this here on the bottom? And then I'll draw the CH2 dash. The benzene ring was going to be a small benzene ring on the side, but I made it, and that's it. Phenylalanine. Okay? So I made I was able to get the amino acids that fulfill the criteria they have. Okay. So we're moving on to the acid-base behavior of the amino acid. And we're told here, the pH at which the amino acid exists as the Zwitter ion is called the isoelectric point. So I am not great with terminology, so what I try to do is read into it and understand why they picked that word exactly versus a different word. So iso usually means same, and then electric here is talking about charge. Okay? Now, these charges aren't necessarily the same, but the way I look at it is you at least have a positive and a negative charge, right? It's more like a neutral form of the amino acid. So we're dealing with amino acid after the hydrogen here has reacted with the base portion, right? After the acid has reacted with the base, what we have is the ionic form. And in the ionic form, you have a negative charge here and a positive charge. So the molecule, the amino acid, is neutral. So this is essentially the neutral point or neutral form, also called the isoelectric point. Okay, the neutral form, as we can see it here, is the one that's called the Zwitter ion. And the neutral doesn't mean no charge present. You just have equal but opposite charges. Zwitter ion. Okay, so we're going to try to find a pH where the amino acid exists as a Zwitter ion. For the most part, the pH is very close to neutral. So please notice that this pH they chose here, this pH is very close to neutral. And the neutral pH is a pH of 7. So if the amino acid is in the environment that's close to neutral pH, it exists as a Zwitter ion. Okay? So we can see right here, this amino acid exists as a Zwitter ion when the pH is close to 7. And remember, it has no net charge. It's considered, neutral, as in no net charge. Okay? So the amino acid can exist at different forms depending on the pH of the aqueous environment. So we're going to be looking at low pH, high pH, and what that looks like. So when the pH is low, this is what it's showing right here. This symbol means pH is low, less than. The carboxylate ion gains a proton, and the amino acid has a net positive charge. So for this to make sense, imagine you take this amino acid in this form and move it to an environment, okay? And in this environment here, we have a low pH. Now, because we haven't taken 14, 12 before we took this class, like in the majors class, let me fill in some gaps, right? Low pH is equal to high H plus concentration. So when they're saying low pH, they're saying that you took this amino acid and put it in an environment where there's a lot of H pluses. Well, I'm going to use opposite attract to explain what's happening here. Since the environment is rich in H+, the H+ cannot do anything with this ammonia end or the amine end because they have the same charge. You see that right here? So they can't do anything. But the H+ can come and neutralize this end by reacting with it. So the H+ comes over here and neutralizes the end. So in a rich hydrogen ion environment, also called low pH. So low pH means rich hydrogen ion environment. The H+ neutralizes this end, and this is what we end up with. We now end up with this end being truly neutral, having no charge, but this other end, the positive end, remains positive. So in a low pH, the overall amino acid now has an overall charge of +1. The +1 comes from here. When it was a Zwitter ion, it had an overall charge of 0. Okay, that was not mentioned here, but I'm mentioning it right now. The overall charge was 0 because we had one negative charge, we had one positive charge, they neutralized each other in that sense. But now one side has been neutralized by the environment, the other side remains positive, so now the overall charge is positive. You want to be aware of that. Okay? What if the environment is not acidic and it's basic? When you have a high pH, that's what this is saying, high pH. This time, high pH is synonymous to or equal to remaining rich with OH minus, these negative ions called the hydroxide ions. So that's high pH. Okay? So when the pH is high, the ammonium cation loses the proton and the amino acid has a net negative charge. Let's see how this happens. So in this case here, the OH minus is trying to find something to react with. It cannot react with the negative part of the amino acid because they are alike. They have to be opposite to attract each other. So it can't go there. So it ends up going over here. But what it ends up doing, it removes the hydrogen. So the OH minus removes an H plus, right? By removing a hydrogen ion, guess what it forms? Forms water. Does it show that right here? Oh yeah, here. It forms water. But in the end, this that was positive now becomes neutral because a hydrogen and a positive ion are gone. So what we have here is a neutral amino end. This part is neutral, but then the hydroxide end remains negative. So the overall charge on the amino acid is now negative. So we're looking at just two scenarios here. A scenario where the amino acid ends up positive because the positive end doesn't become neutralized, right? And then a scenario where the amino acid is negative because the negative end doesn't get neutralized. Okay? So when I was trying to memorize this, which I was really struggling, I don't memorize things well at all. Right now, it appears I memorized it. No, it became very familiar that, yeah, it bypasses my logical processes now. But back then, I was thinking, so it's almost like the negative environment makes the amino acid negative, like the environment. Like they say, your environment changes you. Oh, you've changed. I know it was hard for me to memorize it, but I could think about it that way. The environment made the amino acid negative. So the environment was like negative, is high pH, then the amino acid had a form that was more negative. I know I can remember all that, but I can't memorize. My brain is just special. And on the other side here, the environment is positive. The hydronium ion or the hydrogen ion is positive. So in this case here, the amino acid takes the positive form, that form. Okay? When the environment is neutral, the amino acid is like the environment, neutral or having no net charge. So you see how my logic kind of worked? Kind of. So they'll be asking you there, right there, they'll be asking you, draw the structure of the amino acid glycine at each pH. We have close to neutral, we have acidic, which is rich in H+, or a basic, which is rich in OH minus. So this is simple, right? The picture they have here, this will go with pH equals 6. Because remember, pH equals 6 is close to neutral, and so you want your amino acid to have overall no charge. So I'll say here, net charge is 0, okay? Now I'm going to draw the same amino acid with a pH of 2. So pH of 2 is acidic, right? So the pH of 2, which is acidic, remember that's going to be rich with H plus. So with that one, remember that this part here gets neutralized, and then the other part remains as positive. And you want your amino acid to have an overall charge that matches the environment. Okay, so here net charge plus 1. Okay, so yeah, the crazy stories I was telling weren't so crazy after all, right? Not so crazy. It did help me remember. Even when I got anxious, I was able to remember. Okay, because there was a story there. It wasn't just information. There was a crazy logic that made sense in my head. Okay, now the environment has changed to a basic environment, right? Basic environment is the environment that's rich in OH minus. The amino acid adapts to its environment. So the negative part is the one that stays, and then this other part becomes neutral, like that. So you can see here, this is negative, this is going to be positive. Net charge minus 1. Okay? Okay, same thing. Draw the structure of the amino acid valine at each pH. pH 6, I'm not even drawing pH 6 because we're starting off as a neutral form, right? You have that, so this will go with pH 6, which is a neutral form. Okay, so that one is done. Now pH 2, same thing. Let me see, can I make this smaller? Oh, this doesn't work. I don't know why the plans I have for this app are just, I should find, so I think I told you guys about the Good Notes. Good Notes is similar to this one here, but you pay for Good Notes. Maybe I should pay for Good Notes and maybe you can do all these things I'm trying to get done. Nah, I won't pay for it. I'll keep fussing about this app, but I'll also be glad it's free. Okay, where was I? pH 2. pH equal to pH 2 is rich in H plus, so I want the positive end to remain COOH. And then here NH3 plus CH2, CH3. There are 2 of these. It's a little tedious, but it's not that bad, right? This part of the book, hopefully you realize, is a little bit more tedious, but the concepts are not impossible to learn, right? They're a lot easier than the other part. OH minus, so we want this to be mostly negative, right? So negative end remains negative, then the positive end mellows out. So we have this right here, CH3, 2, right? Okay, so we draw the structure of the amino acid valine at each pH. Which form predominates at valine's isoelectric point? Are you kidding me? Predominates. This one here predominates at the isoelectric point. Because isoelectric point, you don't really have an overall charge, right? So it can't be the pH of 2 or pH of 11 because they have an overall charge of positive 1 and negative 1, which takes away from the whole isoelectric. Okay. Wait, let me check to make sure there's no question. Oh, okay. Hi. I haven't gone over the lab yet, Christina. I'm just not seeing your question. I haven't gone over the lab yet. Do you need me to go over it now? My plan was to do it towards the end because, yeah. Okay. Give me just a moment. So I'm going to take a quick detour and look at the lab. I have the lab right here. Maybe not. Right here. Okay, so oh, well, you typed too slow. Sorry. No, I had all my stuff ready. I was just like looking at this. So, uh, but you can see how what we've talked about is being asked here, right? How does each group, our group, determine if the amino acid is basic, acidic, or nonpolar? Okay, let me see. That's interesting. The lab book talked about nonpolar, but then the textbook didn't, because in the majors class we you talk about nonpolar. So while we're here for number two, the nonpolar ones, are going to be the alkane looking ones, right? Like isoleucine will be nonpolar, leucine will be nonpolar, because these do not have any of the heteroatoms right there, right? Or alanine would be nonpolar. I was wondering why that wasn't mentioned here, and I was trying not to go into it if it wasn't mentioned, but it's mentioned in your lab book. So, yeah, isoleucine, leucine, alanine, these are all nonpolar because the side group is a alkane. Okay, so since I came over here, we'll come back to the lecture. You had a question about, I have forgotten what the question was. Oh, you had two questions about page, was it 4 and 5? The last two pages, the one with the TLC plate and the chromatographic picture. And then your other question was about identifying the amino acids, right? When you had the protein chain. Was that the questions? If I remember correctly? Like how you would answer this question right here? Okay. Yeah, so once you identify the tripeptides, yeah, once you have the tripeptide, you just have to identify which of these peptides are in those tripeptides. So let me start with the chromatography of the amino acids first, and then I'll go ahead and look at the abbreviation. So we'll kind of be jumping ahead, to talk about that. But let me answer this part first here, and then we'll go through that. And then what I'll do is, because this is jumping ahead, it will not make sense right now. So let me go ahead answer this part because it doesn't have anything to do with what we're doing right now. And then I'll answer this part here, the abbreviation of the tripeptide when we get to it. Okay. So remember, your lab, we're not doing actual wet labs. So in a way, the direction they're asking you here is supposed to be something you're doing after you've done the wet lab. So what I did was I provided the answer for you. When it says draw your chromatogram, including the colors, or attach an original paper here, technically that part is done for you. Okay, so this part here is done. Okay. Now, from here, you're supposed to calculate what is called the RF values. Now, I was looking at a previous lab. I had you guys do something like this in the previous lab. I think it was carbohydrates or something else. Where I had, no, it wasn't carbohydrate. It was the acids with the aspirin and the analgesics. I had you guys work on this, but I realized something. The height of the solvent was provided for you. So when you're figuring out the RF values of any of these amino acids right here. So yeah, this right here is a chromatogram that is used to essentially separate mixtures. Okay, it can be used to separate a mixture, it can be used to identify an unknown. In the context here, it looks like we're using the chromatogram to identify an unknown. And so we're looking at phenylalanine, alanine, glycine, serine, lysine, asparagine. So these are the known amino acids. These are all known amino acid. And then we have an unknown. And so what happens in the actual experiments is this piece of paper, you'll put drops of the chemical you're analyzing. So you put maybe 5 to 10 drops right here of phenylalanine. Do the same thing with alanine, with glycine, serine, lysine, asparagine, and the unknown, whatever the unknown is. The unknown will be a mystery. And then you will place, between each drop, you will make sure the drop of chemical dries out on the paper. You don't want it to make a big splosh. You want it to dry out. And then you will place a chromatogram, in this case paper, inside a solvent. And the solvent will then travel up the paper. So here, this is the solvent front. Okay, this is the solvent front. That shows you how far up the paper the solvent has traveled. As the solvent is traveling, it's pulling each of these chemicals. Okay, and the idea is the solvent will have a nature. We don't know what the solvent is because we didn't actually do the experiment, but what we're doing here is the solvent pulls the chemical it matches the most. Okay, so the bottom line here is the solvent matches whatever this chemical is, phenylalanine, the most, and so it pulls it up the most. But without really going into all that, all you have to do here is try to identify what the unknown is by trying to figure out how far up each spot traveled. Okay, so to figure out the RF, you need to know the distance traveled by the spot, which is here. Distance in centimeters, the amino acid traveled is in centimeters. So let me do the first one. Phenylalanine, I guess the color is lavender. Wait, these are different colors? They all look the same to me. I'm like, oh, wow, they're all different colors. No, they all look the same to me. Phenylalanine, let's see. It traveled 4.00 centimeters, right? So it's going to be 4.00 centimeters. And then the solvent, oh yeah, it's provided right here, traveled 5 centimeters divided by 5.00 centimeters. So when you divide these two, you get the RF, the retention factor for phenylalanine. So let me go ahead and calculate that. 4 divided by 5, and I get 0.8. So you try to figure out the RF value like I just did. Take the distance traveled by the solvent, distance traveled by amino acid divided by distance traveled by solvent, and you get the RF value for each of those amino acids. You will compare your unknown with these 1, 2, 3, 4, 5, 6. With these 6, your unknown will be close, maybe not exact, but very close to one of those RF values. So the RF value of the unknown will be very close to one of the RF values of the amino acid. And we're using the RF values to identify the unknown. So whatever it matches essentially tells you its identity. If it matches this one here, if we get a 0.8 here, then we conclude our unknown amino acid is phenylalanine. Okay? So that's the purpose of this. I mean, there's more to the experiment than that, but the purpose here was to use RF values. Now, if you'd done the actual experiment, you would have figured all these numbers out by yourself, but you weren't doing that. So I was just trying to get you guys to come to that conclusion. Since you've done something like this before, you have your RF values. And then with your lab book, I guess you could have read that too. It shows you how to figure out the RF values. So taking this divided by that, you get this number right here. Compare these 6 values you get with the unknown, and you figure out what the unknown is. Does that make sense? And so, yeah. Do you still have a question about this part right here? Oh, I guess that was it for that part. Okay, so for this part here, oh, before I move on, I want to make sure you were okay with the explanation of the chromatography portion, right? If you still have questions, just let me know. Okay, so with this part here, as I said, let me go ahead. I'm so close to the okay, good, thank you. I'm so close to getting to the peptides part. So once I get to that, I'll come back here, and essentially, I guess we'll talk about this part right here. Okay, the 3-letter abbreviation, because all you're doing is technically combining them. And so Yeah, I'll come back to that part. Let me see where my, oh, ah. Okay, so we'll go back here. I think I already worked on this one here. Didn't I already work on that one? Oh, okay. So this part here is very similar to what I just did. So there's no need for me to redo this, right? Very similar. This is a pH equals 6. At 11, this will predominate, and then this one here will be NH2. At 1, this one here will have an H, and this would be as is, right? So I won't go into that anymore. Oh, right here, look, peptides. So with peptides, now we're looking at amino acids being joined together to form peptides or polypeptides. So we're told here peptides and proteins are formed when amino acids are joined together by amide bonds. And the amide bonds are also called peptide bonds. Okay. A dipeptide has two amino acids joined together by one amide bond. So I mentioned this before. It's simple. Visually, when I was looking at this when I was a student, I was very distracted. So I always find anchors. I realize I'm distracted, so I have to find a way to overcome my distraction. So I notice essential atoms follow a certain pattern, NCC, right? And that's how you can tell one amino acid, like where one amino acid ends and where the next one begins. So we have NCC, that's one amino acid, NCC, second amino acid. So we can look at this and say this is a dipeptide. We have two amino acids because we got NCC, NCC, or you can say NC squared. Anyway, NCC is fine, okay? Remember, with your amino acid, you have your central carbon, you have your carbon, a carbonyl carbon on the one hand with the carboxylic group, you have your H, and then you have your amine group, right? And then down here, you have whatever makes this amino acid unique, R, whatever that is, right? So when you define what R is, that will help you identify what amino acid you're working with. And then remember, the dipeptide bond or the peptide bond is also the amide bond, the bond between the carbon and the nitrogen, okay? Okay, so here we have a tripeptide. It has three amino acids joined together by one, not like a whole amide bond, but here's one amide bond. Yeah. Okay, so NCC, one amino acid, NCC, second amino acid. So here we have three amino acids, right? Then the R parts will be different to tell you you have three different amino acids. Oh no, I hope everything is okay because I see the quality. Okay, the quality said it was bad. Anyway, so polypeptides have many amino acids, while proteins may have 40 or more. So imagine these poor chemists who are not very, I mean, they're very hard working with the chemistry, but when it comes to math and writing a lot of things, they get tired. That's why we have those shorthands, right? So we're told here the amino acids can combine in this way. So here we're seeing alanine combine. Okay, I'm a little rusty in the name, so I should think a little more. Yeah, alanine and serine are combining, right? And this will be called combined. This will be called alaser. Oh, hold on. My signal keeps going in and out. I don't know what this is about. Okay, I hope it doesn't bump me out. Anyway, yeah, this will be called alaser, right? So yeah, so it as they come together, as the aluminum and serine come together, it's a dehydration synthesis again. So water has to be lost in their coming together, right? So two hydrogens get removed from here. And please notice they're using the Zwitter ion form to combine these two. So two hydrogens go off with one oxygen, but then only one bond is formed between carbon and nitrogen, right? So these two go off and they make, of course, a water molecule. And then the nitrogen that lost two hydrogens is now neutral, And then the carbon that lost one oxygen bonds with the nitrogen. And so this is where the new amide bond is made. Amide bond / peptide bond. Okay, Alistair. So, oh, we haven't started naming yet. Oh, there it is, Alistair. So, yeah. Let me see. It shows that my signal is getting better. Okay. As long as it doesn't interfere with the video, I think that's fine. As long as you can see. If you lose my screen, just let me know, because that means the connection got very, very bad. Okay, so when we have many peptides, one of the things that scientists want to know is which peptide has got the amine end as the free end. So the amino acid with the free NH3 group is called the N-terminal amino acid. And this is usually written on the left. I'm like, seriously, all the time? This makes it so much easier. The amino acid with the free carboxyl group is called the C-terminal amino acid. And this is usually written on the right. So terminal usually means like end, right? Like in a train station or plane, terminal means you've arrived, it's the end. Yeah, so N-terminal usually is the amino acid where the nitrogen is the one that's poking out. It's the furthest right element, right? And then C-terminal, we're looking for the carbon, carboxylic acid carbon, the alpha carbon. That's the carbon, well, carboxylic acid carbon. That's what I should call it. This is the C-terminal. So you got a C-terminal amino acid, N-terminal. So you want to make sure you can identify that. That's really not that bad, right? Just which side has the carbon, the carboxylic carbon on the furthest right. That will be this one here. And then the left side will be the ammonia, nitrogen, right? So as far as naming this dipeptide, if they use the full name, it's alanylserine. So what they do here, if you notice, the original name of this is called alanine. I-N-N. I mean alanine as an I-N-E as a suffix. And then this one here is serine. But if you're naming it as a dipeptide, then you take the alanine, I-N-E, replace the I-N-E with the Y-L, kind of like the methyl group, right? So the I-N-E gets replaced with the Y-L. It becomes alanyl. And then the last name, the serine, the terminal amino acid, it retains its regular name. So alanylserine. It's a little tough for me to say that. Alanylserine. Okay? But if you're told to do this in shorthand with a 3-letter abbreviation, it's ALA-SIR or ALA-SIR, whatever. I mean, either one works. Okay? So here we're told, for the given tripeptide, identify the amino acids that form the peptide. Okay? Label the N and C terminal amino acid. Provide the tripeptide. Oh, sorry. Name the tripeptide using the 3-letter symbols. Ugh. Okay, we can do this. No need to panic. This is essentially, hopefully, answering your question, Christine. Yeah, Christine. Pronouncing all these words. So I'm trying to find my amino acids, right? NCC. This is one. NCC. Here's the second one. NCC. That's the third one, right? Now I have to find what my side groups are. This is my side group. I'm finding the side groups that are poking out from the chiral carbon, or that carbon that's stuck between the carbonyl and the nitrogen, right? So this one here. Oops, this one here. Let me do the red so y'all can see. Okay. So this is my side group, and then this is my side group. So now I'm going to go back here. I already see one, that one there. This is phenylalanine. And the 3-letter abbreviation for this one here is phe, or F for 1-letter abbreviation. Okay, the one where the side group is H. Oh, right here, same on the same page. This is glycine, right? So this is called glycine. 3-letter GLY or C. Okay. Now I need this one here. CH3 twice. Not that. CH3. Not this. I've seen that somewhere. I don't remember. I mean, it's got to be down here somewhere. Oh, there. Valine. My goodness. I had all these memorized at some point. I forgot. I don't teach this class enough to remember these things. And I'm not good at remembering things just on the fly. I have an idea. I had a logic to remember this, y'all, but now I'm like, ooh. Okay. So we have to name the tripeptide using 3-letter symbols, okay? So if we're using this as 3-letter symbols, that's actually easier than if we're using this one here, right? If we have to use the whole name, that would be a little bit tougher. Valine, yeah. But 3-letter symbols, that's easy. VAL-GLY-PHE. Just write the 3-letter symbols and then dash 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 between each 3-letter symbol. Okay. I was thinking they were asking us to do this part here. That's a little bit trickier. They just showed this to you here. Okay. So let me see. Oh, we have another one that we're going to be working on here. Oh, I didn't do all the parts. I identified the amino acid. I didn't label N. This is good because of the nitrogen. This would be the N terminal. This is going to be the C terminal. Okay. Oh, let me check to see if there are any questions. Okay. Over here, I'll start with the easier one, which I forgot last time, which is the second one here. N terminal, C terminal. Okay, that part. Now we have to find these. Remember NCC, NCC, NCC. We have to find these amino acids based on the identity of these right here. And then that one right there. Okay. So let's see. This is carboxyl group. So I'm thinking, let me go back to the last page. That was a carboxyl group right there. Aspartic acid. Aspartic acid. ASP, comma, D. Then this one here, CH3. CH3, where is that? There, alanine. Alanine. ALA. A. Okay. This one right here. Weird. That's this. Isoleucine. ILE. I was about to say L. No, this is I because leucine is L. That's I, right. 3-letter abbreviation ASP-ALA-ILE. Right, that would be the name of this. Okay. Now, I was looking at this one earlier saying identify the N and C terminal amino acids in each of these. You would have to draw them out. I mean, here, since the way they draw it, they always have the N on the left. This is where the N terminal will be, and the C terminal will be here. So, yeah. For that one, this is the N terminal. I write it as N term. And this is going to be the C term. C term. Yeah, by the time I got here, I was like, yeah, this is exciting as it isn't easy, but it's also kind of boring because it's not really challenging. But it's nice to have a break, right? It's nice to have a break. C terminal and terminal. But for that reason, it wasn't my favorite section of chemistry because I'm like, this is not that challenging. I'm not a glutton for punishment, but I'm like, it's not as exciting either because I'm like, I like the stories. Don't get me wrong, I like the stories, but I'm like, there's no mystery. There's not a whole lot of mystery. Ooh, okay. Let's see. So I'll get to this point and I'll go back to the lab and make sure I've answered the question, right? Okay, so here we're told identify the N-terminal amino acid in the tetrapeptide. Ooh, there's 4 of them. Okay, so alanine, glycyl, leucyl, methionine. Okay, so methionine has its regular name. This will be the C terminal, right? Terminal. So I'm going to write this here. Methionine is a C terminal amino acid. Why? They always said they put the N1 to the far left, the C1 to the far right, the C terminal, right? And then the N terminal, you want to take the name, so it's ala, alanil. Replace the YL with INE, alanine. For some reason, I struggle to say that one. Alanine. There. So the N-terminal one is the alanine amino acid, and the C-terminal one is the methionine. Okay. So let me see. Yeah, the first one, the answer will be alanine. Write the peptide using 3-letter symbols for the amino acid. Okay, so we're going to take this one right here. Let me see if I can erase it. And then write the 3-letter symbols. I won't even try to do this. Let me see how far I can get from memory. I'm trying not to add another page here. Okay, so ALA is for alanine, ALA dash glycine, GLY dash leucine, LEU dash methionine, MET. Yeah, alanine, ALA, glycine, I saw it somewhere, GLY, leucine, LEU, methionine, MET. Yeah. Okay. So that will pretty much be the 2-letter symbols for the amino acid. If they ask for 1-letter symbols, just use the 1-letter symbols. You know, A, G, L, M. Yeah. Okay, for this one here, it says identify the individual amino acids in each dipeptide, okay? And then name the dipeptide using 3-letter abbreviation. So once again, NCC, NCC, the other one. So using the side group, CH3, where is CH3 here? Oh, this is going to be identify individual amino acid. This is going to be alanine, right? Then this one here, isoleucine. Yeah, they're kind of hanging around this area more, right? And then the second one, let's see, and then we'll kind of go back and look at the lab and make sure we got the lab covered. This one has a benzene ring and a hydroxide, so I'm going to go ahead and find the benzene ring with the hydroxide. That's not that one. The hydroxide group was with serine. There, tyrosine. Tyrosine. Then this one here, valine. Valine. Okay, that right there. Okay, so I'm supposed to identify the individual amino acids. I got that part. And then name the dipeptide using 3-letter abbreviations. Oh, this would be ALA. Isoleucine is what? ILE. Let me make sure I'm not butchering this. Yeah, ILE. And then tyrosine is TYR, I think. Let me make sure. Yeah, TYR. Valine is VAL. Yeah, using the 3-letter abbreviations. That would be that. Okay, so here's a sign for me to go back to the lab to make sure we have answered everything in the lab. Where's the lab? Okay, I know it's somewhere here. Oh, sorry. I just remembered. It's on my iPad. That's why I'm like, I can't find it. I have a system and I forget the system. Oof. Okay. So yeah, for your lab, now back to the lab. For this part in the lab, once again, use the three central atoms, right? NCC to identify the amino acid, the cutoff point for the amino acid, right here. NCC, another amino acid, NCC. Okay, so we have three amino acids, says so right here, tripeptide. We're gonna use this thing I have right here to determine which side group this is. Our side groups, oh, that's the thing in chemistry, right? Everybody doesn't obey the same rules. In this case here, our side groups are up, not down, right? If you can see, they're right here, they're up, not down. So in the lecture information, the side groups are pointing down. In the lab, they're pointing up. So let me find the first side group that has an OH in it. Okay, the ones that have OH, oh, right here, serine, right? CH2OH, but CH2OH. So that one's going to be serine. Second one is just regular H. That should be glycine, right? Yeah, glycine has regular H, so this is glycine. Then this one here should be alanine. Alanine. I might rememorize this again. Nah. I will, but if I don't teach this class for another 3 years, I'll forget them all. So yeah, alanine right there. Okay, so they want the abbreviations for this tripeptide. I'm looking here trying to figure out condensed structural formula. You can condense these side groups, and that's about it. I mean, you could try to draw them in here, but I'm trying to see. With the condensed structural formula, for this part, I think this would be the most challenging part as I'm looking at this. NH3 positive here. You can write C in parentheses CH2OH. So actually, it'll be CH2OH. Yeah, I know as I was moving on, I noticed that we haven't really answered this part here. You can write like this and then do it that way and then continue with the carboxyl CO and then NH and then continue on and on and on. So the condensed, I just worked for the condensed part, which I had skipped over because I was focusing on the other parts. I just worked on this part, that part, that part, and that part. So you can continue on and on until you finish the whole molecule, okay? For this other part that I was working on, SER-GLY-ALA. Then the one letter, I haven't done that part, so SER, serine, will that be S? I'm not, yeah, S. And then glycine should be G, and then alanine should be A. But let me confirm. Glycine is G, alanine is A. Yeah. Does that answer your question, Christina? I want to make sure I've covered all the questions that you have. Hopefully. Okay, great. So, yeah. So I think as we go through the rest of the chapter, it will answer some of these questions that we're looking at right now. So now we're looking over other peptides. So these are biologically active peptides. And these are called neuropeptides. That means they somehow influence the brain, right? These are called enkephalins, and they usually are connected to pain relief. Enkephalins are pentapeptides. So these are short pieces of peptides that have 5 amino acids, and they're made in the brain, and they act as natural painkillers and sedatives by binding to pain receptors in your body. Addictive drugs like morphine and heroin bind to these same pain receptors, thus producing a similar psychological response, but it lasts longer. So most of these bad drugs, these are the ones that are controlled substances, were usually made for good reasons, right? But then they somehow got in the streets and they were now abused, right? But they were originally made to help people out in pain. And so let's see. Enkephalins are related to a group of polypeptides called endorphins, which are known for their pain-reducing and mood-enhancing effects. They usually say, go work out to get some more endorphins. And then, you have the people who are crazy in the gym and trying to get, that natural high from working out and stuff like that. Anyway, one of the enkephalins, metenkephalin, is drawn below right here, and it's called metenkephalin because on the C terminus of that pentapeptide, we have methionine. So here they have the 5 amino acids attached together. And of course, it's called metenkephalin. Tyrosine, glycine, phenylalanine, and methionine. So you can see the amino acids, hopefully NCC, all the way to the end. Okay? And so the other neuropeptide, the other enkephalin, is called leuenkephalin. And why is it called leuenkephalin? This group of chemists, their logic is so different, but they're very simple yet, neat. Why? Because you have a leucine on the right. Okay, so you have a leucine group right there, so they call it leuenkephalin versus metenkephalin, but they have similar functions in the body. So we're told here, label the 4 amide bonds in metenkephalin. What N-terminal amino acid is present in both enkephalins? Oh, this has to go back up here, north. So find the 4 amide bonds in metenkephalin. Okay, that won't be hard to find. There's 1, 2. So I'm just trying to find the bond between the C and the N, right? The one that joins them together and yet separates them. 1, 2, 2, 3, and then here 4. Okay, right there. Yeah. Okay. And then what else am I supposed to do? Scroll. What N-terminal amino acid is present in both enkephalins? N-terminal. Let's to the left, right? So let me start with the top one. I'm usually going somewhere and I get distracted. You probably see me being distracted. That's why I have to be super organized to deal with my natural distraction. I get fascinated so easily by things, and I'm like, oh, look at that. Okay, so this amino acid right here, this is my side group. So this is the alcohol. So I'm thinking it would be next to the serine group. Let me go find the serine. Is it right there? Yeah, tyrosine. This is tyrosine. Oh, it's written right here. Duh. Same thing with that one, tyrosine. Okay, so they both have tyrosine. So I can go down here and say they both have tyrosine amino acid as the N-terminal amino acid. Okay. And then we're moving on to different amino acids that do different functions in the body. Now we're looking at peptide hormones. These are amino acids that act like hormones: oxytocin and vasopressin. Oxytocin and vasopressin are cyclic peptide hormones which have identical sequences except for 2 amino acids. So everything else is similar except for these 2 amino acids right here. Isoleucine and leucine are present in oxytocin, while we have phenylalanine and arginine present in vasopressin. Okay, but every other part of the molecule is similar. So what do these do in the body? Oxytocin stimulates the contraction of uterine muscles to help with labor and pushing the baby out. And then it signals for milk production once the baby is born. So it helps with milk letdown. Like once the milk is produced in the breast, it gets to come out of the breast because oxytocin is helping to contract those muscles to let the milk out. Okay, so it's often used to induce labor. Vasopressin is an antidiuretic hormone that targets the kidneys and helps to limit urine production to keep the bodily fluids up during dehydration. So vasopressin helps your body to not face dehydration. Okay. Okay, now we're moving on to different forms of proteins. We have here for proteins, you got primary structure, secondary structure, tertiary structure, or quaternary structure. Okay, so primary protein structure the primary structure of a protein is a sequence of amino acids. So this looks more like a pearl, like a string of pearls, right? You have a bunch of amino acids joined together with peptide bonds to form a string of pearls. And the bonds essentially are at 120 degrees. Let's take a moment and see. Oh yeah, our carbon, this is not the chiral carbon. This is a carboxyl carbon. Has a double bond here, so we have 3 electron groups. For that reason, the bond angle here is 120. They're referring to that. Okay. So because of that, your protein, your primary protein, has a zigzag arrangement. It looks like this: zigzag, 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 NCC, zigzag, NCC, zigzag. The central atom have that zigzag arrangement. Moving on. Then we have a secondary structure of protein. The secondary structure of protein, what we see here is a 3D arrangement of localized region of the protein. We tend to have 2 major formation or 2 major arrangements in the protein. Those 2 stable arrangements are alpha helix and beta pleated sheath. So we're working towards that. So what makes these shapes possible is because in the protein molecule, we have hydrogen bonding. And the hydrogen bonding, so we're going back to that organic part, right, occurs between the NH group of one amide and then the carbonyl group of another. So the NH group is trying to attach itself to the carbonyl group. So the H tries to attach to O. And when this happens, kind of like with a DNA molecule, when this happens, the 2 pearls or 2 strands of pearls now begin to coil around each other. And you have the alpha helix coil and the beta pleated sheet. Okay. So the alpha helix, essentially we have a peptide chain that twists into a spiral. So it looks kind of like a phone. You'll see how it looks. It's spiral, spiral or spiral, whatever. And then the beta pleated sheets, you have strands of pearls. I'm trying to use the analogy that are kind of lined side by side towards each other, but they have a kink. And so the easiest way to illustrate this is just to show you what it looks like. I feel like my words are not doing this description justice. So if you have a primary protein, these look more like straight. In the secondary protein, we now have an alpha helix that looks more coiled like that. Okay, so the coiling is possible because you have the hydrogen bond formation that actually holds the structure in place. And the hydrogen bond forms between the nitrogen or the hydrogen here and then the oxygen once again in the carbonyl. So these hydrogen bond with each other to keep this structure in place. If you do something to break this hydrogen bond, this converts back to the acyclic straight form. Okay, so the secondary protein can be converted to the primary protein sometimes by heating and breaking these hydrogen bonds. Okay, this is showing you the beta pleated sheet. So to form this, you have a bunch of primary primary proteins next to each other. Then they try to interact with each other side by side. In the process, they form these kinks that look like chevron design, the zigzag pattern, right? You see that in there? It's actually a zigzag pattern. I'm trying to draw the zigzag. I'm not very good at it. The picture is actually distracting me, but yeah, trying to draw the zigzag pattern. And so this kink that we see, it looks like pleats, so it's called the beta pleated sheet. And you have many of these primary proteins side by side influencing each other, cross interacting with each other. So if you can zoom here, which I think I can do that, I can show you how the hydrogen, this is a nitrogen, this is a hydrogen, interacts with the oxygen. So once again, this is due to hydrogen bonds. The secondary structure we see here are possible because of hydrogen bonding. Okay. So once again, 2 forms, alpha helix, beta pleated. They do a better job at illustrating this. I don't think I did a very good job at it, but you can see it. Okay. So secondary structure. Most proteins have regions of alpha helix and beta pleated sheet, as well as regions that cannot be characterized. They kind of look like they're primary, right? They look a lot simpler. So to show you these regions in a simpler way, they use a ribbon to show you, a coiled ribbon to show alpha helix, and then this arrow to show you beta pleated sheets, and then the random region that looks like a, you know, a primary protein will be the random region right here. Shorthand symbols called ribbon diagrams are used to indicate these regions of secondary structure right there. Okay, this right here is the atomic model, okay, showing you all the atoms and how they're connected. That is very confusing. I think this picture is a lot better, so we'll spend time here. You can see these are the alpha helix. This is the beta sheet, right? And this is the random region. So this protein has got 3 different types of amino acids and 3 different types of proteins, essentially, arrangements, okay? So after we've seen that, we move on. We're told label the regions of secondary structure in the following protein ribbon diagram. Okay, that's easy to do. The greens are alpha helix. This part here is just random. And this is beta pleated. As I said, this part is really not that bad, right? Okay. So now we're looking at, we're getting towards the end. Tertiary structure is a 3D shape adopted by the entire peptide chain. So now the peptide chain coils upon itself, and it kind of coils even more. And so now we have a maximum hydrogen bonding. So we're told here to maximize hydrogen bonding with water, the nonpolar side chains are stabilized by London dispersion forces in the interior of the structure. So when you take this protein and put it in the water, the protein rearranges itself to maximize the hydrogen bonding. But in doing so, it keeps the nonpolar sides of the chain away from the water. Remember, the molecules have that behavior to protect the nonpolar side. They push it kind of away. So here we're seeing polar functional groups can be hydrogen bonded to each other. Amino acids with charged side chains are attracted by electrostatic forces or interactions. Disulfide bonds form covalent bonds that stabilize the tertiary structure. Bottom line, the more complex the structure, the more bonds are taking place. So they're telling you all of this can be going on in a tertiary or quaternary structure of the protein. The more complex, the more coiled it looks, the more bonds you have going on to keep the protein in that shape. Okay. So we have a lot going on here. So they're showing you here the dotted lines are signifying the hydrogen bond. So you can see right here, hydrogen bond, dotted lines, hydrogen bond again, dotted lines. These are London dispersion force. Why? Nonpolar. So you see how these interact with each other via London dispersion force? Because both are nonpolar. This is charged and this is charged. So this will have to be, electrostatic attraction is the same thing as ionic. Electrostatic attraction is a term used to describe opposites attracting. Okay. Here we have H and O, or O and H, hydrogen bond. H and O, hydrogen bond. That makes sense. Let's see. This is called disulfide bond because you have 2 sulfurs attracting each other. This one here you can see, right? London dispersion force, because once again you have 2 nonpolars attracting each other, London dispersion force. Then what keeps this coily is hydrogen bonds within the same protein attracting each other, keeping it coily. Then finally here you have hydrogen bonds. So for us to have this tertiary / quaternary structure, there's a lot of bonds holding the structure together. Okay. So what's the difference between tertiary and quaternary structure in the protein? It has to do with the number of bonds, right? Technically, we haven't seen the quaternary structure here. So yeah, see, that question should have come in later on, because if you look down here, this answers the question. The quaternary structure of the protein is the shape adopted when 2 or more folded polypeptide chains come together. When we had the most folded polypeptide chain, that is tertiary. But quaternary is when you have a bunch of these, chains aggregated or brought together, and they essentially form the quaternary structure. Tertiary is just one chain coiled on itself like that. Okay, remember, primary is just like that. Secondary, you have the coil, alpha helix, and then you have the beta pleated sheet like that. It looks like waves. Okay, so you got secondary, tertiary, quaternary, primary. Oops, primary. Okay, so let me go back to the question. I'm done with that part. Which of the following pairs of amino acid can have intermolecular hydrogen bonding between the functional groups in their side chains? Okay, tyrosine. Okay, so if you look at the side group here, COO negative, NH3, H, CH2. Let me see, I have my benzene ring here. I have this OH. Yeah, by having this OH here, this could hydrogen bond with something else, right? Because you have the OH. So 2-tyrosine residue can hydrogen bond. What about alanine and threonine? Alanine and threonine together. Let me find those structures here. So yeah, these two can, but what about alanine and threonine? So let me draw that over here. Alanine, oh, I already see the answer to that. Can these hydrogen bond with each other? Oh, let's see. NH3 positive. This is CH3. This is LDF, y'all. This is alanine. What about threonine? Threonine. I haven't actually drawn that today, have I? Threonine. I don't see them hydrogen bonding with each other because while threonine has the ability to hydrogen bond with something, this is LDF, right? So CH, I have a OH here, and I got a CH3. Yeah, this one can hydrogen bond, but it cannot hydrogen bond with alanine. So this is THR. These cannot hydrogen bond with each other. No hydrogen bond with each other. Now, 2 threonines can hydrogen bond with each other. They just can't hydrogen bond with an alanine. Okay, so this one can and this one can't, sadly. Okay, here we're told draw structures of each pair of amino acids and indicate what types of intermolecular forces are present between the side chains. Ooh. Use figure 16.7 as a guide. So what I'm going to do here is I have to add a page. I don't have a choice. So serine and tyrosine. Okay. So I see tyrosine already. I wish I could just copy and paste. Can I copy and paste from somewhere? I don't know. Just starting to feel. How many pages do I have? Okay, I'm getting close to the end-ish. NH3 positive H CH2. Okay, OH. Yep, this one can hydrogen bond. But I'm supposed to serine. Serine is right there. So serine is COO negative H H3 and positive CH2 OH. So this one can hydrogen bond also. So they can hydrogen bond with each other. I'll say here hydrogen bond. Okay. Okay, what was next? So we're done with this. Valine and leucine. Okay, let's see. Valine and leucine. With valine and leucine, let me scroll. Oh, valine is right there. CCOO minus H3N positive H CH2, CH3, 2, right? I already see LDF, y'all. This is LDF. Okay, what about, that was valine. I need to find leucine. Where is leucine? Where are you, dear leucine? There you are. COO minus H3 and positive CH2CH3 2, also LDF. So guess what? Since they both have LDF capacity, that's what they do with each other. The LDF. Yeah, non-dispersion force. They're both nonpolar, right? I have one more to do. One more. And I can move on. One more. Let me see. 2 phenylalanine residues. 2 phenylalanine. Okay. I'm going to draw one and then copy it, right? Because, y'all, this structure, it's not super complex. It's just time consuming. It's tedious. CH2, okay? And I got to draw the ring. I got to draw the bonds and all the stuff and put this right here. So I'm just going to copy this, paste, and then, what did I just press? Did I just press paste image? Right there. Okay. So, whatever the left one does, the right one also does. This right here, come on. I copied you. What is this structure doing up here? I resign. Okay, hold on. I could have sworn I copied this structure and I put it down. Copy, paste. But I feel like when my pen moves, it moves. Yeah, see that? I just saw it do that. Okay, stay here. Oh, this is what it does. That's weird. Okay, maybe I need to move it down. Anyway, bottom line, these two are both LDF and LDF. So that's how they interact with each other, LDF. Okay, they're both nonpolar. Okay, so we talked about this, the quaternary structure containing conglomerates, you know, like a group of the superfolded quaternary structures. Okay, and then they form a complex. Okay, so insulin consists of 2 separate polypeptide chains linked by intermolecular disulfide bonds. Hemoglobin contains 4 subunits held together by intermolecular forces into a compact 3D shape. So here we're told proteins are generally classified according to their 3D shapes. Fibrous proteins are composed of long linear polypeptide chains that are bundled together to form rods or sheets. Fibrous proteins are insoluble in water and serve as structural roles. Globular proteins are coiled into compact shapes that are water soluble. We have enzymes and transport proteins that are globular. Okay, this is just showing you different types of proteins that are structured and packed differently based on their function. And so usually if, in this case, the fibrous proteins, that reminds me of rope, right? They're long, they're linear, they're bundled together to form rods or sheets. And for that reason, they're insoluble in water. Globular proteins, these have different functions. You have enzymes and transport proteins. These are usually traveling to places, and they tend to be globular, kind of like, when it says compact shapes, I'm thinking circular. They look like pods, right? Pods transporting different chemicals. They're usually round, and there's something inside of them in their core transporting different chemicals from one place to the other. So we're now going to be looking at hemoglobin and myoglobin. These are globular and conjugated proteins, meaning they contain both protein and non-protein components. The goal here for hemoglobin, as it says here, the non-protein component of heme is an iron 2 ion. Okay, so you know how if you suffer from low blood or a low blood count, they tell you, oh, you're anemic, you need to take some more iron. You're thinking, well, blood isn't technically iron. but what they're trying to do is to help to build up your hemoglobin, which iron is an ingredient for, or I guess it's a chemical present in hemoglobin. Iron binds to oxygen in the bloodstream, and then hemoglobin, we're told, transports oxygen to wherever it's needed in the body. Or if needed, myoglobin stores oxygen in the tissue. So myoglobin essentially resides in the tissue, and it stores the oxygen in the tissue. So here we're seeing the heme unit. There is the iron right in the middle. So these are your proteins right here. 1, 2, 3, 4, right? So this is your globular protein, where you have groups of protein essentially transporting something or holding on to something. In this case, iron 2 is the iron holding on to these 4 units of protein. Okay, myoglobin has 153 amino acids, and it's one polypeptide chain. Here's the structure right here. Myoglobin essentially is holding onto the heme unit right here. And of course, you have your iron right there in the middle. Okay. So moving on, hemoglobin has got 4 polypeptide chains. 2 of them are called alpha. To help you see this, they show you these in different colors. 2 of them are called alpha, 2 of them are called beta, and each of them carries a heme unit. Okay, you can see the heme unit right there. There's the heme unit. And the polypeptides help to carry the heme unit. And within the heme, you have more nitrogen, right? You have more nitrogen setups right there. So it's really, yeah, it's interesting. Okay, so now we're talking about hemoglobin and myoglobin. And so carbon monoxide is poisonous because what it does is it binds to the iron 2. Carbon monoxide competes with oxygen to bind to iron 2, right? And so carbon monoxide is very poisonous because when it binds to iron 2 iron, oxygen cannot bind behind carbon monoxide. So hemoglobin complex with carbon monoxide cannot carry any oxygen. For that reason, the cells die from lack of oxygen, and this is how people get poisoned by carbon monoxide. Okay? So let's see. Yeah, we're getting close to the end. The rest of this is mostly just biology, and then we're going to get into some hydrolysis here, breaking down the bonds and everything. So protein hydrolysis involves breaking the peptide bond by adding water and acid, like we've seen before. If forming the dipeptide or tripeptide involve removing of water, if you want to break those bonds, you have to bring back the water that got lost. So hydrolysis of amino acid in a protein forms an individual amino acid of the primary structure. In the body, the enzyme pepsin in gastric juice cleaves some of the peptide bonds of large proteins to make smaller peptide chains. In the intestine, the enzyme trypsin and chymotrypsin, or called renin, man, I had to learn all this in biology, hydrolyzes the remainder of the amide bonds, resulting in individual amino acid. Bottom line, amino acid is broken down in your body. It's broken down in your stomach and your intestines, okay, by different enzymes versus water and sulfuric acid. This time, sulfuric acid isn't present in your body, so enzymes have to be used in this place. Okay, moving on. I'm thinking back here, and I think I misspoke when I said, yeah, I'm saying nitrogen, so I'm thinking, yeah, we're not talking about the type of compounds that are here in the heme group. So even though I think I did mention amino acid, these are not exactly amino acid. We're not talking about these kind of compounds here. But bottom line is we do have these 4 repeating units in the heme group. There's a lot of 4s in the heme group. And the 4 repeating units then exist inside 4 right here of the protein units in the heme, right? Hemoglobin. So yeah, hopefully that clears things out. But yeah, you have the heme unit here. We have the 4 polypeptide chains in the amino acid. Okay. I'm actually impressed. I'm still awake. Okay, so here we're trying to break down the amino acid, right? Break down the protein to get amino acid. So just like we did before, count NCC, and then that's where the bond will break. This is where the bond will break. And so you have to bring back what was lost, right? Remember, on the right side of your amino acid, you have that C terminal. So you're bringing that back in. So when this bond breaks, you're bringing back in the bond, then the oxygen. Then the other end, when that breaks, you're bringing back the N terminal end, NH. And I mean, it's H3N plus, right? That part comes back in after you add water. The oxygen comes back here, and then 2 hydrogens come back here. Then it continues, okay? So you want to be aware of how to form products once you break these bonds right here. Here it says, draw the structure of products formed by hydrolysis of each tripeptide. I'm just going to pick one, y'all. I'm just going to pick one because whatever I pick, the last one. Actually, you know what? No, the first one. Let me pick the first one because I'm like, I think these are easier to draw. This first one. Come on. Okay. Sorry. it's just getting to that part. Are you kidding me? Hold on. I've been trying to copy this so many times and something else keeps showing up. Okay. Draw the structure of the products. Okay. So let me scoot down here. So we have alanine, leucine, glycine, right? They want us to draw the structure of the products when these are hydrolyzed with water and then the relative enzymes. So for alanine, let's see. Hold on. So we got carbonyl right there. H3 plus N. Alanine has this. So I have to draw the tripeptide first, right? This is my ala part. I need to find my leucine. Where is leucine? N H C H C double bond O N CH2 CH CH3. Hold on, man. Sorry, y'all. I'm slowly. I'm just like my brain is slowly going on power save mode. I'm like, no, come back. I'm almost done with this. Okay, so this is my leucine. I'm struggling to do the structure, and after that, I have my glycine. Glycine should be N C C double bond O O minus. So glycine has an H here and it has an H here. So what I'm gonna do here, let me see if I can do a shortcut with this. We're gonna be breaking these up, right? Let me see if I can draw them from here. Okay. Okay, this is my second one. Okay, maybe I can make this smaller. And then I'll find my third one. Copy. Okay. I'll draw it to the right. Okay, hold on. Ooh. Lone pair, lone pair. Okay, lone pair, lone pair, lone pair. I have not been drawing my lone pairs, y'all. Imagine they're there, right? Okay. So for this one here, we're bringing in water, right? So this one becomes minus. This one here becomes, the H's add up here. The H's add up here, and this one becomes O minus. Yeah. So this is what the 3 amino acids look like when they get hydrolyzed. Okay. Okay. So we're looking at protein hydrolysis and denaturation of proteins. So the shape of the protein is due to the interactive forces that exist between the protein. We've said that before, right? Denaturation is the process of altering the shape of a protein without breaking the amide bond. So we're breaking the intermolecular forces, but not breaking the actual bond that makes the protein a protein. Okay, so we're gonna go from the most complex structure to the most basic structure. That means from quaternary all the way to primary. So here, if you have a coiled globular protein and you apply heat, then you end up with loose coils and loops. Okay, it's kind of like when you flat iron your hair, you're breaking the intermolecular forces, but not necessarily breaking the forces that make your hair. Unless you apply too much heat, then you're gonna be breaking the forces that make your hair completely, right? Okay, just want to make sure there's no question here. Okay, so high temperature, acid, base, and even agitation can disrupt the non-covalent interactions that hold a protein-specific shape. Think about it. This is true of your hair. Your hair does have a lot of protein in it, right? Mostly protein. And if your hair has coils or curls or it's wavy, that's due to the intermolecular forces. So when you apply heat or acid or base, it does change the curl pattern of your hair, even if it's for a little bit. If it's heat, just heat, then adding the heat will change the curl pattern. Then when you wash your hair, you kind of restore the intermolecular forces that were there before. Denaturation often makes globular proteins less water soluble. And they talk about eggs right here. So albumin, the major protein in egg white, is denatured when the egg is cooked, changing from clear, colorless to opaque and white. So the other way to deal with eggs is by applying acid to it, like we're told here. You can apply acid or base. So sometimes they try to denature the egg by putting it in acid, and they say here it's denatured or cooked. I'm like, no, cook it with heat, not with acid. I know I read it in the PowerPoint slide here in the textbook, but no, with heat, please, with heat. Okay, so we're to the final stage of this lecture. I don't think I need this page anymore. I'm sorry, y'all. I've been talking for a while. It's like, whoo. Okay, I'm trying to hang in there. Enzymes are proteins that serve as biological catalysts for reactions in all living organisms. They do increase the rate of the chemical reactions, but they themselves, the enzymes, are not changed. Enzymes tend to be very specific, preferring a very specific substrate that they're going to bind to. Okay, each enzyme tends to catalyze a specific reaction. The name of the enzymes have a prefix related to the substrate, but then they end with the suffix ase. So like lipase is an enzyme that catalyzes reactions involving lipids. Protease, enzyme that catalyzes reactions that deal with proteins, right? Anyway, and then like lipase, hydrolase. A cofactor is a metal, ion, or organic molecule that is needed for the enzyme catalyzed reaction to occur. So the cofactor kind of helps out the enzyme. Okay. So now we're looking at examples of different enzymes, right? And so we're told here NAD plus is a NAD plus, I call it NAD. NAD plus is a cofactor or enzyme helper that oxidizes into pyruvate with the aid of enzyme lactase dehydrogenase. So the enzyme lactate dehydrogenase is an enzyme that tells you essentially what it does. Okay, the lactate is the name of the substrate. Dehydrogenase is the type of reaction it actually speeds up, and of course, ase is the name of the ase is the suffix used for the enzyme. Okay, so here we're kind of going to biology territory, not my strong suit, you can tell. Because there's no mystery to figure out. You're just learning names and stuff. Okay, here, the coenzyme is here to help the lactate dehydrogenase do its job. So what they're going to do here is NAD will take off one hydrogen, another hydrogen will come off two, and we go from the alcohol lactate into pyruvate. And this is important ultimately for pyruvate is an important chemical for the Krebs cycle. Okay, so we're going to talk holistically though versus this. This is very specific, right? This is just trying to make a point here. Holistic though, we're going to try to see how enzymes work. The point that was being made here is that enzymes are named systematically based on the substrate they work on and the type of reaction they actually speed up. Okay, so moving on to how enzymes work. Enzymes tend to be larger than the substrate. So here, right here is the enzyme and here's the substrate. An enzyme contains an active site that binds the substrate, forming a complex between the enzyme and the substrate called the enzyme-substrate complex. So the enzyme is kind of like a host. It's an avenue. And then the substrate is drawn to the enzyme. And when it binds to it, the enzyme has an active site that binds to the substrate. So remember, enzymes go with specific substrate, right? So they're compatible. The substrate comes here and binds, and when it binds, the enzyme does what the enzyme is supposed to do, either bring substrates together or break them apart. In this case, it looks like it's going to break them apart, right? Yes, I was right. Once the reaction has occurred, the catalyst then releases the products. There. Sometimes the opposite is happening, where these are coming to the enzyme, combining, then leaving off together. So it's not always breaking them apart. It can be bringing them together. Okay? Two models have been proposed to explain the specificity of the selectivity of the substrate from the enzyme. Remember, the enzyme has a very specific site. So there's certain substrate that it can't really help because they don't fit, they're not compatible. One is called the lock and key model that states that the active site is rigid cavity with a specific shape. To react, the substrate must exactly match the shape of the active site. For example, right here, okay, this is our enzyme, and these are our substrate. So for them to react, they're coming in as individuals. They're going to combine. For them to react, the substrate must match the active site of the enzyme. They come together. They're now one, form a bond. They go off together thanks to the enzyme. This is called the lock and key model. So the idea is the substrate fits the enzyme like a lock will fit a key. Or should I say the key fits the lock, right? That's a lot better. Okay. Over here, we have something called the induced fit model, which states that the active site is somewhat flexible versus having a more specific shape that can adjust and fit a variety of substrate shapes. So there are two different groups of scientists who have two different views of the same occurrence in the body. Some say the enzyme's active site never changes, it's always fixed, selecting certain substrates over others. Some say, nah, the enzyme is kind of flexible, adapting to whatever the substrate needs. So in this case here, the induced fit model says the enzyme's active site is a little bit more flexible. So here's the enzyme. Once the substrate comes in, the enzyme adapts. So here you see the enzyme adapting to the substrate. Okay? So here, when we deal with enzyme, there's something called inhibitor. There's an inhibitor. An inhibitor is a molecule that causes the enzyme to lose its activity. The inhibitor can compete for that site on the enzyme. So right here, this inhibition can be reversible or irreversible. A competitive inhibitor has a shape and structure similar to the substrate, so it kind of poses as a substrate. So it actually competes with the substrate for the binding, for the substrate to bind to the active site. So now the substrate has competition from the inhibitor, okay? And here we see, this is what the reaction looks like when the substrate comes to bind to the enzyme, right there, breaks off. And here is the inhibitor. We can tell it's not the substrate because the rest of the molecule looks different, but it's posing like the substrate because the active site matches, right? They're compatible. So if the enzyme comes and binds to, if the inhibitor comes and binds to the enzyme and doesn't go away, then when the active site, oh my goodness, I'm almost done, y'all. 'Cause my words are getting worse. I know what I'm trying to say, but I'm not getting to say it. Okay. When the substrate comes in, what it finds is the inhibitor bound to the enzyme via the active site. And it's like, okay, well, now the substrate has nowhere to go. So in this case, the enzyme has bound to the inhibitor. If the inhibitor doesn't leave, now the substrate is competing with the inhibitor. Okay? There's another one called the non-competitive inhibitor. I'm not pro-inhibitor, but if I was pro-inhibitor, I would be for this inhibitor. This inhibitor is like, no, I'm not going to lower myself to the standard of the substrate and even compete with this. This is a non-competitive inhibitor. This bonds to the enzyme, but it doesn't even bond to the active site. This one here bonds to a whole different site, but it controls everything from a whole different position. An example of the non-competitive inhibitor. Here's the active site, and it's like, nah, I don't even have what it takes to bind there. I'll come bind behind here, but I'll change the active site. Now no substrate can bind to this active site of the enzyme. And this is what happens. When the inhibitor is bound, the active site shape changes, right? And so no substrate can bind to it any longer. No substrate will fit over there. Okay, so now we're moving on to, we haven't done focus on health, so now we're finally going to that. Using enzymes to diagnose and treat diseases. Certain enzymes are present in higher amounts in particular cells when something is going on. Well, in general, right? If these cells die, so we know that certain cells have certain enzymes in large amounts. If these cells die or rupture, these enzymes are released into the bloodstream and can be detected. Enzyme levels are then used to detect a disease. So if say a lot of this, my goodness, if a lot of liver enzymes are found in the blood, that means the liver cells are dying or something is wrong with the liver, right? So here are examples of enzymes that communicate to doctors there's something wrong with the patient. If the creatine phosphokinase, if a high concentration of this is found in blood, that indicates the patient is having a heart attack. Heart attack, right? If a lot of alkaline phosphatase is found in the blood, that indicates the patient has liver or bone disease. If a lot of acid phosphatase is found in the blood, that indicates that the patient may have prostate cancer. This is so sad, but this is a reality. This is how the scientists can tell, in this case, doctors can tell of a patient's condition. So over here, we're told, use the given representations for an enzyme, substrate, and inhibitor to illustrate the process of a non-competitive inhibitor. Like I said, if I was pro-inhibitor, this is my favorite mode of attack because this inhibitor is like, I'm not even struggling to compete. The inhibitor comes over here, doesn't even compete, and changes the shape. So now the shape goes from being this shape to being a different shape. Now the substrate can't even fit in there. That's it. Inhibitor, non-competitive, has done its job, and that's the end of it. Here we're told, use the given representations for an enzyme and substrate to illustrate the difference between the lock-key model and the induced fit model of an enzyme. Well, we know with lock-key model, with lock and key, substrate has to be compatible with enzyme. Okay? I'll write up here. With induced fit, enzyme adapts to fit substrate. Okay. Oh, wait, is this the last slide? Oh, last 3 slides. Okay, we're close to the end. Woo, I'm struggling, but I'm trying to hang in there. Okay, so enzymes are very specific in their active site. They're also specific in the activity as far as temperature and pH is concerned. Okay. So here at lower temperatures, enzymes and substrate move slowly. And so, yo, hold on. Let me tell you. Okay, yeah, it's my brother. Okay, at lower temperatures, enzyme and substrate move slowly. It takes longer for the substrate to bind with the enzyme. Therefore, at a high temperature, higher, not too high, at an optimal temperature, substrate and enzymes are able to bind, resulting in a chemical reaction. When the temperature is too low. So here we have a temperature on the x-axis versus the rate of the reaction. Temperature is too low, the molecules are moving slowly. Both substrate and enzymes are moving very slowly. Temperature optimum somewhere here, the reaction is maximum. Temperature is too high, and enzymes begin to denature and then destroys the active site. Therefore, substrate cannot bind to enzymes. Okay? Moving on. pH. Same thing with pH and enzyme activity. The activity of the enzyme decreases as the pH decreases below 8 and decreases as the pH increases above 8. So you have the happy medium, right? Where you can see the activity of the enzyme decreases when the pH is very low, when the pH is very high. Now this one here, when they're talking about the enzyme activity, this enzyme here that prefers a pH of around 8 is in a very specific part of the body. I can't even remember what it is. I know it's not. I think it's the part of the body that's right after the stomach. Because the stomach is very acidic. And so the enzymes in the stomach will prefer acidic environment, low pH. The ones right after the stomach are the ones that prefer basic environment. Because I remember learning this in biology, thinking, so the food that comes from the stomach is very acidic. It goes to the basic environment to neutralize it, then it goes to the rest of the body, right? So yeah, this is the enzyme they're referring to. This is not true of all enzymes. Enzymes are different and they work in different environments. This particular one we're talking about prefers a slightly basic environment, okay? And so we're told pH effect on enzyme activity. The activity of different enzymes vary depending on the pH of the environment. That's exactly what I said. So what is the optimum pH for the activity of chymotrypsin? Where's chymotrypsin? Oh, right here. The optimum pH I'm thinking is around pH of 8. pH equal 8. Does the enzyme activity of cholinesterase increase or decrease as the pH increases? Actually, at first, the pH increases, activity increases, and at some point beyond 8, actually maybe around 7, yeah, around 7 and above, the activity does not change. So I would say here, for this one here, increases at first, then activity is not influenced by pH. Yeah, first it increases and at some point it just stops being influenced by pH. Does the enzyme activity in papain change with changing pH? Papain, no. Activity is independent of pH. It does not even recognize the activity is the same regardless of the pH, right? Papain, cholinesterase, chymotrypsin. And we made it to the end, guys. Thank you very much. I'm going to close quickly right now because I'm so, yeah. I did take a medication that made me a little bit drowsy, but we were able to make it to the end. I hope I pressed record. Yeah, I did. But this is the end, okay? Y'all have a nice evening.